about 17,500 miles per hour.
Houston, we have a problem. A circular problem.
Centripetal force is the force that keeps objects moving in a circle, and it's always pointed towards the inside of the circle. But if you remove it, the object is just going to keep moving in the linear direction that it was before. Take this box on a car seat, for example, and if you take a sharp turn, there's not enough friction, which is the centripetal force in this case, to keep the box moving in the direction that your car is, so it slides in the linear direction that you were just moving. Centripetal force can be calculated through the mass of the object times its centripetal acceleration. And centripetal acceleration is the rate of the velocity's change. And I know what you're thinking, the speed isn't changing, but its direction is. And velocity is a scalar quantity, so it has a direction and a magnitude. So centripetal acceleration can be found in the equation v squared over r, and it is the rate at which the object's velocity is changing as you're rotating it. Take this bucket of water, for example. As you rotate it, the centripetal acceleration is what's providing the change in direction, and the force of tension in the string is the centripetal force that keeps it moving in a circle.
The apparent weight of an object in a circle is determined by how much of the normal force that object is experiencing. For example, when the car on this Hot Wheels track is at the bottom, its apparent weight is greater. This is because it has both the normal force and the centripetal force acting on it. On the other hand, when it is at the top, its apparent weight is less than the actual weight of the object. This is because only the centripetal force is acting on it rather than both the normal and the centripetal. This is also why when you are on a roller coaster, you feel super heavy at the bottom, like the whole world has come crashing down on you, and when you're at the top, you feel like you're gonna fall out. Also, the centripetal force and your apparent weight is what keeps you going in the circle rather than just falling.
The period of an object is the time it takes for the object to complete one revolution around the circle, and is equal to 2 pi over the angular velocity. The frequency, which is the inverse of the period, is how much of the revolution the object completes in 1 second. Take this clock, for example. When the second hand moves, it is completing 1/60th of the circle, so its frequency, which is measured in hertz, is 0.0167 hertz. Its period, the total time it takes to complete one revolution around the circle, is 60 seconds, or 1 minute. The circumference of the circle has an impact on the period because as the circumference decreases, the object has less distance to travel. And at the same speed, it will take less time to complete the smaller circle.
One example of period and frequency that can be seen in the real world is the classic game of tetherball. When the game first starts, the string is the longest it can be. This means that the period is going to be the largest because it has the most circumference to travel. As the game progresses, the string gets shorter and shorter because the string wraps around the pole. This causes the circumference that the ball has to travel to decrease. Because circumference and period have a direct relationship in the equation 2 pi r over linear velocity, the period will decrease as the game goes on. Inversely, from start to finish, the frequency or the distance traveled by the ball in 1 second increases. This is because period and frequency have an inverse relationship.
Newton's law of gravity is the force of attraction between all objects in the universe. It is equal to the gravitational constant times the product of the two masses over the distance between them squared. Take this egg drop, for example. Because the mass of Earth is so large and the distance between the two objects is so small, the force of attraction between the egg and the Earth is very large. In a very similar way, the Earth exerts a force on the Moon, and this force is what keeps the Moon in orbit around the Earth.
Fly me to the moon, let me play among the stars, and let me see what spring is like on Jupiter and Mars.
A satellite is a projectile that is moving in an orbit around another object. Satellites are kept in orbit by the centripetal force that the gravity of the planet it is orbiting exerts on it. The mass of the satellite does not affect its velocity because the velocity of a satellite is equal to the square root of Newton's gravitational constant times the mass of the Earth or whatever planet the object is orbiting over the distance between the two.
Furthermore, if two objects are equal distance away from the object they are orbiting, their speed is the same regardless of their mass or size. This is seen in the equation period equals 2 pi times length divided by gravity, as previously mentioned. It reveals that only the mass of the object at the center is taken into consideration and not the mass of the object orbiting it. Additionally, the farther from the center an object is, the longer its period. Take the ISS we are on, for example. Its distance from Earth is 240 miles, so its period is 90 minutes. But let's say the ISS was 480 miles from Earth. Its period would be much, much larger. This is because distance and period have a direct relationship, meaning when one increases, so does the other.
Liar! Keeps the moon in orbit around the moon.
Yeah, I'm gonna go and have this.